today's lesson is going to be on vectors. This is section 6.4 in your book, and we're just going to get into the basics of vectors here in trigonometry. For those of you that go on to take physics, you'll get into this a little deeper. We'll do one application problem here on my examples on the videos. We won't get into a lot of applications with them, but as you get into physics, you'll get into more and more. But first, what we need to do is we need to have a little background. So you need a little terminology here. Okay, you need a little terminology. So first, what is a scalar quantity? What is a scalar quantity? Okay, well these are basically physical quantities that can be measured by a single number. So a scalar quantity, for instance, would be something like length, area, and volume. These are examples of scalar quantities. They're something that can actually be measured by a single number. Now, many physical quantities, though, aren't measured by a single quantity like length, area, and volume. So we have things like velocities and forces and displacements that can't be described by just size, okay? That's the difference in these. These right here are described by size, okay? Some of them can't be described by size. And these are called vector quantities. Vector quantities. And basically, a vector quantity requires both size and direction, okay, to have a complete description. Now, the size that we have here, another name that you're going to hear me call this a lot is the magnitude. This is the magnitude, okay? So it needs both magnitude and direction to be a vector quantity. Now you see a lot of these in the engineering field, but in a practical kind of situation, if you have any family members that have been in the National Guard or in military at all, if they've ever flown in a helicopter, helicopters use vectors to be able to fly. Okay, a lot of time airplane pilots will use vectors, so they are they're often used a lot in aviation. So, but in this section, what we're going to do is we're going to talk about vectors in a plane, and we're going to discuss the magnitude and something called a unit vector. But let's continue on with a little bit of vocabulary. For instance, what is a vector? What is a vector? Well, if you have a plane, if you have your coordinate plane, then if A and B are 2 points in a plane, okay, so this is point A, this is point B. If they're 2 points in a plane, then a vector from AB looks like this. A vector from AB looks like this. It's the arrowhead is right at B, okay? And we write this in terms of vectors. We write a vector. This would be called vector AB. Vector AB. Now A right here is called the initial point. B is called the terminal point. Okay? A is called the initial point. B is called the terminal point. And so we can have vectors all over the coordinate plane that have the same magnitude and same direction as this vector. Okay, so we could have one up here that has the same magnitude and same direction. This could be CD, so to speak. Okay, So in other words, it's the same size and it's going in the same direction. So now, if you translate vector AB about the origin, okay, if we let the initial point start here at the origin, and let me change color so we can see this differently than the rest. If we let the initial point start here at the origin, and it's the same size and direction as AB, except we're going to call this O and P, okay? If the initial point starts at the origin, this is said, if it's a translation of AB and the initial point starts at the origin, we call this the standard vector. The standard vector. It's the same size and magnitude as AB, but its initial point starts at the origin. Okay, same size of AB. Its initial point starts at the origin. So essentially, I like what your book says about this. Essentially, what you have here is you've got a bunch of. I like to compare this to fractions. Okay, this is we could say that this is the fraction. This is an example now. Don't get confused. This is a real life example I'm trying to relate here for you. This is, let's say this vector represents the fraction 4/6, and this represents the fraction 6/9. Okay? Well, both of those fractions are equal to one another, aren't they? Both of those fractions equal what? Both of them equal 2/3. So both of those vectors are the same. They're just in different places. Now what the standard vector is the 2/3. Okay? The standard vector is the 2/3. It is the reduced form. Okay, basically. It is the simplest form of that vector. It's the one from which all other vectors of equal size and magnitude are based. Okay? So that's what our standard vector. Hopefully that fraction. Don't get confused with that. Just a real life example to kind of relate to you what the standard vector means in terms of these other vectors, okay, that are equal size. Alright, so if you have vector AB here, okay, if you have a vector AB, okay, we can write this vector in terms of coordinates, and we write it like this. This is x, y, would be the coordinates of this vector. Now, what you got to realize is this. Notice that those are not parentheses, okay? So don't get these confused. This tells you that it's the coordinates of a vector. It's basically what it's giving you here is it's giving you the coordinates of point P, okay? So if we're looking at the standard vector, we know the standard vector starts here, right? We know it starts at 0, 0. So you don't have to have those coordinates. This is giving us the coordinates of the whole thing as it goes through P. It's essentially what this coordinate means. So now, how do we get x and y? Well, for instance, if point A is the point x sub A, y sub A, and point B is the point x sub B, y sub B. So these are just two different points here, okay? If this is the point of A and this is the point of B, to find this vector form here, x, y, well, x is going to equal x sub B minus x sub A. And y is going to equal y sub B minus y sub A. Okay, so this is how we would get those coordinates of that vector AB. Alright, so let's look at an example of this. for instance, if we're given that the geometric vector has AB, has an initial point, the initial point A is 8, -3. And the terminal point B is 4, 5. Okay? What I want to do is I want to find the standard vector. Find the standard vector OP for AB. In other words, what that's saying is find the coordinates of P so that these two vectors are equal. Okay? Find the coordinates of P so that these two vectors are equal. So in order to find the coordinates of P, again, what we have to do is, remember, this is x sub A, y sub A. This is x sub B, y sub B. So to find our vector, well, we're trying to find vector OP. To find vector OP, we have to do, the x coordinate, remember, is going to be 4 minus 8, which is -4. And the y coordinate is going to be 5 minus -3, which is 8. So our standard vector OP, is -4, 8, the coordinates of P. And essentially, folks, let's make sure we're getting this straight, because I don't want you to be confused. I mean, I know it's easy just to plug in and get this. This is not hard, just plugging in a formula. But I want you to understand the formula, because OP here, when a moment ago when I was writing this to describe our AB, this is essentially giving us the standard vector. Okay, this gives us our standard vector. Now, this gives us the point, these right here, of point P. Because we already know point O. Point O is the origin, 0, 0. So this right here, essentially this right here is the coordinate of point P. Okay, so I want you to understand what that is. It's essentially the coordinate of point P, but we just write it in vector form right there. Okay, we write it in vector form. All right, so now oftentimes you are going to see vectors written in boldface typing, but when you're writing it out on a sheet of paper, it's kind of hard to tell boldface typing on a sheet of paper like that, handwritten. So make sure you include the arrow above the vector. Okay, that's always going to be the way to make sure you get it right. If you have some vector AB, A and B are called, excuse me, the pen's writing slowly. A and B are called scalar components of that vector. Scalar components of that vector. Okay? So, two vectors, vector U is AB, and vector v is CD, those two are said to be equal if their scalar components are equal. So in other words, if A equals C and B equals D. Now, we have something called the zero vector. The zero vector is just the vector at 0, 0. And it's denoted by this. We just write 0 with a vector over it. That is the zero vector. That's the shorthand for the zero vector. All right, so now you heard me talk about magnitude earlier. The magnitude of a vector. So if we have vector v equals AB, okay, then the magnitude is going to be denoted like this. The absolute value of v. The magnitude will be the absolute value of v. Now your question should be, how do we get v? Well, it's going to be the absolute value of v equals the square root of a squared plus b squared. So that's how we get v. So it's the absolute value of v, whatever that happens to be. So magnitude, the magnitude is the length of the standard vector associated with v. So it's going to be the length of the vector associated with v, okay? That's what the magnitude is. It's going to be the length or the size of that vector. And because length is, think about it, when you measure something, you don't ever measure a negative length. Length is always positive, right? So this is why we must take the absolute value of v in case we get a negative number with that square root, because remember, plus or minus the square root. In case you get a negative number, because you're in a negative quadrant or something like that, because these are all drawn in quadrants, remember. So if you're in a negative quadrant, then what we say is this. We say that you have to take the absolute value so that that distance is always positive. Okay, so that distance is always positive. Now, let me show you something that might make the whole process a little more simplified for you. Where students tend to get confused is when if I say, okay, here's AB, okay, here's the vector AB, and we've done our subtraction and we get negative 4, 8 like we did a moment ago, okay? So if this is the standard vector, it's at negative 4, 8. So here's what we know about that. Let's just suppose this is the standard vector for a moment. Let's suppose this is the standard vector. So if that's the case, if this is the standard vector, here's what we know. We know that the initial point A is going to be at the origin, and excuse me, I drew that in the wrong direction. I am sorry. Let me redraw this. So don't pay no attention to that. Here's our standard vector. So we know we know that this point is 0, 0. This vector would go in this direction. The standard vector would be in that direction. Now, how do I know that? I know that because of this right here. What the standard vector says is that this is 4 units to the left, 8 units up. So when you're solving for that vector quantity here, okay, when you're solving for that like we did in the last example, that's what that represents. Your end result represents 4 units to the left, 8 units up. So it's telling you kind of how you need to draw the standard vector. And so what that means is every vector off of that would be just the same. So if I were to draw a vector here, and I know it's not, but let's just suppose this vector CD is the same size and everything as this one. Well, I have to draw this in such a way that no matter what these points are here, it doesn't matter what this XY is here, it doesn't matter what this XY is here. When I do my rise and run, so to speak, it's not rise over run, so don't get that confused. When I do my the difference in my X coordinates and the difference in my Y coordinates, I still have to be the same as the standard vector. So it's the same. We do that so it's the same length, and I have to. It has to be in the same direction. Okay, in the same direction. So no matter where I draw a vector, if I draw it the same as this standard vector, it has to be 4 units to the left, 8 units up when I draw it, no matter what point I start with. No matter what initial point I start with, it's going to have to be drawn 4 units to the left, 8 units up. I hope that makes sense. On page 385, there's a very good picture of what I was trying to draw there, that no matter, once you get the standard vector like that, no matter where you draw any other vectors of same size and magnitude, wherever it starts, wherever that vector starts, it has to be 4 units to the left, 8 units up. That's how we get the same size and same magnitude. And I hope that makes sense, because this is a lot of terminology to throw at you at one time. I promise you, don't get wrapped up if you don't understand the terminology yet, because it will come to you as we work some of these problems. So don't let it confuse you if the terminology is messing up with you right now. All right, so hopefully you understand that, and I'll see you in the next video.